Hello, everybody. Mr. Hennon here. I'm just going to continue with this idea about thermal conduction. This one's a little bit different, so I wanted to kind of break this up a little bit because I thought it might make it a little bit easier if you saw it in bits and pieces. So we have a wall, and a normal wall is going to have plywood on one side here, and then it's going to have some kind of insulator, some kind of, fiberglass or probably that's going to be the most obvious. And then it mentions here that the thermal conductivities of the insulation and plywood are respectively 0.03 and 0.08 joules per second meter degree Celsius. So the lower one is going to be the insulation here, and the higher one is going to obviously be the plywood, and then the area of the wall is 35 square meters. It wants you to find the amount of heat conducted through the wall in 1 hour. So the idea is we're going to try to figure out the heat flowing through here. And then they give you some information in the problem that the inside of the house, we're going to try to keep it at a constant 25 degrees Celsius, and the outside of the house is cold. It's at 4 degrees Celsius. Now, when you look at this, your first instinct is, oh, I've got my equation. Q is going to equal little k, the thermal conductivity, times area, times my change in temperature, times the time, divided by the length. And so we're going to do this in 1 hour. So our time is going to be 3,600 seconds. It's not a problem. And they give us the area. So this is the area because that's the cross-sectional area of the wall. It's the heat's flowing through all of that as it gets through there. Change in temperature, you're like 25 minus 4. That's easy. That's 21 degrees Celsius. I'm good to go. But then you're stuck here because we have a couple of things that are going to throw us off. We also have the lengths. We know the thickness of the insulation here is 0.076, so basically 7.6 centimeters, and the thickness of the plywood is 0.019 meters. So your instinct is, I'll just add them up. That'll be the total thickness. That's the thickness that it has to go through to get all the way through. And that's true. But what do I do with K? And your first instinct is maybe just like length, I'll just add them together. So if I have insulation and plywood, wouldn't the total be just the sum of the two? But if that's the case, then you've basically created a material with a higher thermal conductivity by putting two materials together that are lower thermal conductivity. In other words, you've insulated it more, but you actually have increased its conductivity. That doesn't make any sense. So then the idea is, well, maybe it's the difference between them. Maybe I subtract them. But again, that doesn't quite make sense because then if I had a piece of insulation with another piece of insulation, I would subtract them, and wouldn't that give me a conductivity of 0? And I don't think that's, or maybe it's some kind of average between the two. But I would think that the thermal conductivity would have to at least be whatever the insulation is. It would have to be something smaller than that, surely. So you kind of get stuck. You're like, I don't know what to do. Well, here's the key idea. If you notice in this picture, it shows the heat and it's flowing through here. So heat has to flow through here. And since go back to electricity, since there's only one path for this heat, it has to go through the insulation and then through the plywood. It's kind of like these two materials are in series with each other. And if there's only one path, there can only be one current, one heat flow. And so in this particular case, the heat flowing through the insulation has to be equal to the heat flowing through the plywood. And so we're going to use that to help us out, that the heat between these two has to be equal to each other. Then I can plug in the equation for the insulation. That's the Ka delta T over L, and set it equal to all the information for the plywood. And you're like, but I don't have all the information. Well, what we're going to actually find, and I'm hiding it right now, is we're going to find this interface temperature. What is the temperature at this interface between these two materials? I know it's 25 to 4 here, but across just the insulation, what is the temperature difference? Across the plywood, what is the temperature difference? So I can plug in all my information here. I know the thermal conductivity, I know the area, and I know the change in temperature and the time. But here's one of the things. If you notice, they didn't actually put in the area or the time because they're the same. So I can actually cancel out the areas. I can actually cancel out the times. I don't need those right now. And so what I'm going to eventually solve for is T. Now, if you notice on the left side, I took 25 minus T because 25 is going to be the high temperature. T here is going to actually be at a lower temperature. So that's going to be the lower. I always take high minus low. Over here, the T is going to be at a higher temperature and 4 is going to be your colder. So I took T minus 4. So always make sure you're doing that. You have to kind of switch them. And then the idea is let's solve for T. When you do that, you will find that it's 5.8 degrees Celsius. So the temperature at this interface is 5.8 degrees Celsius. Now, key things with that you'll notice is when you actually have a higher thermal conductivity, the difference in temperature across there is actually going to be smaller. They actually are inversely related. So a higher thermal conductivity causes a lower change in temperature. Now, the other thing that's affecting it is the length of it or the thickness of it. So it doesn't have much thickness to actually lose that temperature, so to speak. So that's why it's also pretty small. You only have 1.8 degrees Celsius. And then a lower thermal conductivity, a smaller thermal conductivity actually has a greater change in temperature across it because it's insulating better. So it's actually has less flow. So because of that, now I have information I can put in to actually find this heat. I can put in the 25 and the 5.8, and I put in my time, put in the area of the wall, put in the thermal conductivity and the thickness, and I can find Q. I could also do this with the wood if I wanted to. In other words, I could put in its thermal conductivity of 0.08. It's also 35 square meters. It actually is going to go from 5.8 to 4. But it's still also going to do this 3,600 seconds, run out space over here, and then divide by the thickness of that plywood, which was the 0.019. And when you do that, you should actually get the same answer for it. So I wanted to bring that up, that when you put more of them together, you layer this insulation, it's going to affect what kind of result you get. And what you have to find is that interface temperature in between the different pieces to actually find what's going on. You could work on trying to figure out what kind of complete combo this would be. So if you wanted to take this and come back and figure out what K would be for a total temperature difference of 25 to 4, you could, but there is no good, easy way to combine these thermal conductivities. You really have to find this temperature interface. There's a problem on your set of problems that I want you to do to try that out. Here's a little concept to finish things out with. So we know refrigerators are trying to remove heat by a cold refrigerant fluid that's actually flowing. We're going to talk about that. That's thermal convection because you're actually having a moving fluid, but then they're touching something. And so it asks here, decide whether the plate should be made from aluminum or stainless steel, whether the arrangement works better or worse when it becomes coated with a layer of ice. So the idea is we want heat to flow through to the aluminum. So we need basically this refrigerant to go through here, and that's where the cold is, and we want heat to flow out. So we need this kind of flow of heat. And so the idea is what would happen if this has a layer of ice versus the aluminum. But really what we're looking at with this one is what kind of numbers do we have for these thermal conductivities. So if I go back to my thermal conductivities here, aluminum is 240 here. It's not too bad. If this was stainless steel, they mentioned, it's only 14. So 14 is a lower thermal conductivity. It doesn't conduct heat nearly as well as the aluminum. And then ice down here is 2.2. It's even worse. So what you would definitely want is you would definitely want aluminum, not stainless steel. And then when you get that iced over, it's even going to be worse. You basically are more of a resistor than a thermal conductor. And so the more covering of ice you get, the harder it is for that heat to flow out. And that's what you want. You need that heat to flow so you can actually cool the insides because you have the refrigerant moving through there. So just a neat little concept to kind of look at as you're looking at these different thermal conductivities. We're going to be working on some problems. I'm looking forward to taking a look at some of these later in the week and see how things go. Hope you enjoyed this edition of the Henstitute.